Hi everyone, my name is Mir and I look after the sales engineering and support for North America. And today my topic is about architecting 3forge to achieve better performance. Now, every application eventually hits a wall. The data will grow, the users will multiply, and what you built during the launch will start to slow down. Now, today I'm going to show you 6 different patterns to make sure you never hit that wall. The 6 different patterns are worker and distributor, hub and spoke, sharding, direct archival, timer sync, and web scaling. And now the best part here is to achieve all of these patterns, you don't need to rewrite the application. These are mostly configuration driven, so you're just architecting around it. Now, before I dive into the details for each, let's talk about what are we actually solving for. So in real life, when your application gets into a production state, you sometimes see that the data volume grows over time. Then as the data grows, your processing power should also increase. Next, you have different teams working on the same instance, but then they require some isolation. They want to build their own things different ways, but they all want to rely on the common set of data. Sometimes you want to achieve horizontal scalability because your volumes are growing massively. Then you have different dashboard that is trying to reach different data sources at the same time. You want to make that process efficient. Then you have something called end of day archival job that is becoming a bottleneck. And you also have end users who don't want to tolerate any downtime. They want high availability. So the patterns I'm going to talk about today, each of them will map into one or more of these problems here. So let's first start with a pattern called worker and distributor. The idea here is simple. You basically separate the processing from distribution. So you have one center that's responsible for doing a lot of heavy computations. It can ingest data from different sources. Then it's going to do some data enrichment, aggregation, joins, filter, etc. So that's your worker center. Now, you have this other center called the distribution center, which whole job is to distribute that data to the end users and other downstream system. So the key concept here is the worker center works and the distributor center distributes that data. Now, in order to set something like this, let's see how the setup looks like. First, you have this worker center. Now, the key point here is you don't need to replicate all of the tables in the worker center to the distribution center. You only replicate the ones that's necessary for the user to be. So here, as you can see, although I have a bunch of tables here, I'm only replicating these two to the distribution center. And I do it by using something called replication. So this is my distribution center, and this is my worker center. Only 2 tables are being propagated to distribution. And then that's where the end users and other system can read the data. Now, why is this architecture powerful? It's powerful because now with this approach, you reduce the write log contention. The worker center is doing all of the heavy computation, it's doing all of the writing, and the distribution center is only serving all of the reads very efficiently. You can spin up one or more of these distribution centers, so you can scale up to n number of distribution centers. So if you want to spin up centers that are localized for a region, you could do that very easily with spinning up more replication and more distribution centers. So that process is entirely configuration driven. The schema and the worker center and distribution center will look different. Here, it will look very simple because it does not need to know about how the data is being arrived at the distribution center. Let's talk about the second pattern, which is hub and spoke. If worker and distribution center is about separating processing from distribution, hub and spoke is about separating central ingestion from the data distribution. So here you have a hub center that acts as the central ingestion layer, and it basically takes in all of the data and sends out filtered subset of the data to n number of spoke centers. So this is your hub center, and this is your spoke center. Now let's see how we can implement this architecture. Okay, so here I have my hub center in one hand. On the other hand, I have a bunch of spoke center, SP1, SP2, SP3. Now the next step is to set up a relay in between that will be responsible for disseminating the subset of data. So inside the relay, you're going to specify your routing and filtering rules. And now to start the data flow, you're going to attach something called relay triggers onto the tables and copy. Once you attach the relay triggers, it will start sending all of the insert, updates, and deletes over to the relay where your routing and filtering logic will be in place, and it will route the messages accordingly to different spokes. Now, what are the benefits of having this architecture? You achieve data isolation on the spokes, so each team can now build on top of their own spokes. The use cases that each team builds can look very different and behave very differently from each other, even though the main source of the data is the same. You achieve load balancing across your different spokes. Each of the spoke centers now just work on a subset of the data so they stay lightweight and performant. This is the important feature of this. You achieve entitlements. People that are developing and using the spoke centers, they don't get to see the entire set of data. So security, enforcement, and compliance is achieved with this pattern. Third pattern is called sharding. This is when your data volume gets massive. The idea here is very simple. You distribute the workload across n number of centers, which are called shards, and then each of the shard aggregates the data into a smaller subset, and then that data gets consolidated back to a consolidation center. Now let's see what it takes to implement the sharding architecture. First, you have your data stream coming in. It could be Kafka, AMS, or whatever your messaging service you're using. It hits the relay. Here, you define your routing rules, basically which messages should go to which sectors. After you define your rules, the messages will flow into the respective shards. Now, this is the key part here. Each of the shard needs to do some sort of reduction on that data set. So usually it ends up being an aggregation. So the data gets reduced on each shard and then gets consolidated back to a consolidation center with the use of replication. Now, what are the benefits of having this architecture? First, you achieve true horizontal scaling with very minimal number of configuration steps. The splitting logic here is flexible. You can make use of our AMI script methods to achieve complex filtering, different formulas, etc., to come up with your sharding logic. What you achieve here is something called real-time union. Even though you're working across massive amount of data sets, you have a real-time unified view here. You can build real-time visualization. And if you want to take a look at the entire trail of a specific shard, you can always query on demand into each of these. So pattern number 4 is called direct archival. Traditionally, if you want to run an archival job, you would have data landing into our in-memory database. It would accumulate throughout the day. And at the end of the day, you would run an archival job that would take all the data and flush it out to an external database or our HTTP. This process is slow, risky, and expensive. The direct archival pattern flips that around. What we say is instead of running the archival job end of day, you stream that data directly into our HTTP. Now, if you don't have the capability of streaming that data into HTTP, you can also make use of our fast JDBC batch insert method to achieve the same throughput. Now let's see how we can implement this. The steps are very simple. So again, you have your data stream coming in, it hits the relay. Now here you set something called duplicate broadcast. So one copy will end up in the in-memory database and the other copy will get inserted into HTTP. Now the difference here is inside the in-memory database, you would set something called upsert. So you only keep the latest state of each record and HTTP stores the full trail. So you can always get a real-time view of the in-memory database. And if you need to see the full trail, you can query the HTTP on demand, which is designed to return you the query as fast as it can. Now, there are a lot of benefits with this approach because now you are reducing the memory pressure from the in-memory database. Now there lowers risk of data loss because you're not waiting end of day to flush that data out. It simplifies your operation because you no longer have to think about running the heavy archival job. And lastly, the configuration is very minimal. All you need to do is set up the duplicate broadcasting in the relay. Pattern number 5 is called timer sync. If you're building a dashboard that needs to reach out to many external data sources, traditionally you would achieve this by creating data models that would tap into the data source, bring in the data, and then update the visualization. Now, there are a couple of caveats with that approach because each data model brings in the copy of the data to each user session. So it has a risk of duplicating the data, and your external data sources get hammered with a lot of requests. Timer sync approach says that instead of querying the external database with each user session, you cache that data into our AMIDB and then keep that data refreshed by using a periodic sync statements. Let's take a look at how we can achieve this architecture. So here's your center, and here are two external data sources, MySQL and Postgres. And we have something called sync statements that allows you to bring that data from the external data sources and keep a cache inside our database. So inside the sync statements, you can specify how often you want to pull by using a timer. So once your sync statement is inside the timer, every 5 seconds and 10 seconds, the data will be refreshed inside our cache. And then if you have visualization built on top of that, they will reflect accordingly. Now here's a little syntax down here that shows you how you can run the sync statement. So it says sync into the trades table that's here on trade ID. This specifies how you want to do the comparison of the data. So the sync process is delta based. So if you specify how a row can be uniquely identified, the process becomes even faster. It doesn't need to replace the whole data on every refresh. So it can be smart enough to find out the delta and just apply that. So sync into trades on trade ID, and we're saying use ds equal Postgres and execute select start from trades. So select start from trades from Postgres and then sync it into our database. Now with this approach, you no longer need to query the external database. The timer handles that. It doesn't rely on each user session. You can build real-time workflows off of that data. Now you're basically turning your external data sources, which happens to be static, behave like a real-time data source. Same that we're doing here, they're delta-based, as I explained before. Now you only keep a single copy of the data instead of duplicate copies inside the data model. And the whole process becomes efficient both in the center and on the web. The last pattern is called web scale. This is one you want to serve more and more users. So there are two key components that we need to keep in mind. Number one is the web balancer, which distributes the incoming load across multiple web servers. And there's web manager that acts as a centralized layout and preferences storage. Let's see how this thing works. First, you have a bunch of web servers. Then you have a web balancer where you specify your routing rules. So users come in here and the web balancer distributes the traffic easily. And then the web manager here, which stores all of the layout files and configurations. And whenever a user logs in, the web requests the layout and preferences file from the web manager and it distributes that over to you. Now, key benefit here is that whenever a web server goes down, the incoming requests will automatically skip that unhealthy web server, and you're not losing out on your layout file and configuration because web manager acts as a separate box and serves that centrally to different web servers.